Hello everyone, welcome to the Team Colfi presentation on Tropopause location and long-range weather balloon communication. I will be talking for the majority of the time here at the beginning, and then I will hand it off to my fellow group members who will discuss their specific areas of expertise. Looking at the outline for today's presentation, we're going to go over the project goal, our theory behind the project, our experimental setup, our results and data, and the possible experimental improvements that could follow. Starting with the goal of our project. The goal of our project is rather simple. We wanted to establish a long-range communication system for a weather balloon. And on top of that, we wanted to transmit all data and even, hopefully, video live down to a ground station. Our first step was to create a long-range network system that was capable of transmitting data down to a ground unit. We then moved on to step 2, which was utilizing an Arduino system and a Raspberry Pi, which we will talk in greater detail later. Step 3 was to use graphical analysis to obtain the results of all of our data. I understand I haven't gone into too much detail over this project as a whole, so we're going to start at step 1, which was the long-range communication system. Here I'm going to hand it off to my fellow group member, Brad.
Hi, my name is Aaron Watson. For my part of the presentation, I'm going to be going over our graphical analysis, our data, and how all this compiles together to give us our goal of the experiment, which is to find the location of the Tropopause using graphical analysis in our data collection. So for our first collection of data, we're going to be looking at the total data of the experiment done, which is from the initial launch height of about 200 meters to our final launch height of about 30,000 meters. Now, when you look at this best fit line, it doesn't fit the total overall curve of the data collection very well. It follows it pretty well at first, but once it gets to the altitude that it reaches about midpoint to its lowest temperature, it doesn't follow the curve very well. So we're going to narrow it down further into a better best fit line that better fits the overall data collection. So for our second analysis of the data, we're going to be looking at the area between about 10,000 to 20,000 meters. The reason we chose this is because the tropopause we know occurs at about where the temperature is at its lowest point. And just from looking at the graph, we can see that occurs between 10 and 20,000 kilometers. And it contains the lowest data point, but we can see from our graph that the best fit line doesn't, as well as the previous graph, fit the total data very well. So we can get a better analysis of where the tropopause location is, but we can see from that where it starts to concave up that it doesn't quite fit the data very well. And we can see from our equations here that that occurs at about 15,000 meters, but we know that's not going to be the exact point. So we're going to narrow this down even further in our next graph to find out where that tropopause location is going to be. Now for our third and final data collection points, we're going to look at 12 to 15 kilometers. And the reason we chose this is because it contains the minimum temperature that the data collection reaches in respect to the altitude, as well as the best fit line given by LogaPro fits the overall shape of the data collection pretty well. For this data, to find this, we take the derivative of the equation given to us by LogaPro, take the derivative, find the minimum points for the y and the x, which gives us a value of negative 39 degrees Celsius and an altitude of 13,700 meters, or 13.7 kilometers. And that is what gives us our overall collection for the tropopause. So now let's talk about how this all comes together. In this slide, we can see the graph of our total data collection. And in our previous graphs, you can see it's not a function of x, as in when you travel down along the x-axis, it covers 2 points at the same time. So for our data collection, we couldn't look at the temperature versus altitude graph because there's no data collection that can be done there. But when we're going to flip our altitude and our temperature, as seen in this graph, we can assess better how the two relate to each other. On the right is our data collection from 0 to 30,000 meters. And on the left, you can see the height of the actual locations of the layers of the atmosphere as given by experiments from other groups. And you can see here on our graph that the total shape of the temperature versus altitude fits pretty well with the temperature versus altitude graph on the left. And so that further proves that our data collection coincides pretty well with actual data collection for an experiment like this. So their overall results for this experiment is we compared two different methods of analysis, the temperature versus altitude and the pressure versus altitude. And in the next slide, we're going to look at how those two coincide with each other. So for the last part of our overall results in graphical analysis, we're going to look at an experiment done by the Department of Meteorology and Atmospheric Science. Now, the point of this analysis is not to look at the individual data points of our graph, but the overall shape and curve of the graphs. On the left is the experiment done by the department. On the right are our graphs of graphical analysis. And you can see in the top right is our temperature versus altitude, and the bottom right is our pressure versus altitude. On the left, with our overall graph, you can see with the red line is temperature and the blue line is pressure. And you can see that our pressure versus altitude, the bottom right graph, follows very well with the experiment done by the department, as well as our temperature versus altitude. And we can see that our data points are reliable, they were pretty accurate, and they overall flow well with the method of analysis for this experiment.
I am Brad Thorne, and I handled making the communication system wireless. The first step of making everything wireless was forming a network. We chose to use some Ubiquiti products because a previous group had left one behind. The other one ended up being stolen with the previous weather balloon, but that's a story Christine can tell you. The products we used were the AirMax NanoStation M5 GHz station and an AirMax Lightbeam AC 5 GHz bridge. As long as we were able to set these to the right settings, they were able to form a connection and communicate with each other. To set everything to the right settings, we had to give each unit, the Raspberry Pi, laptop, NanoStation, and Lightbeam, all their own static IP. The static IP is like the computer's address. It just tells whatever network it's on the name. This was necessary to make them communicate with each other, and that's because putting them all on a static IP as opposed to a dynamic IP, which changes, made it so that they were all more or less in the same neighborhood and could find each other easily. So after we actually formed the connection, we just hardwired the Raspberry Pi into the NanoStation, which was on the balloon, and the Lightbeam, which was on the ground, into a laptop through Ethernet cords. This is the same as all four pieces being on the same Wi-Fi network. However, just because we're on the same Wi-Fi network does not mean we have internet access. This does, however, mean that the laptop could communicate with the Raspberry Pi even if they weren't hardwired together. After everything was set up and communicating with each other, we used software on the Raspberry Pi to view the graphical display, pretty much like viewing what your computer's thinking through your monitor. This allowed us to view the serial monitor of the Arduino that had data from our sensors. In the end, there was some shortcomings though. We had random disconnects that we couldn't really apprehend why they were happening. However, we do have a few potential reasons that we thought of. The first one is the power supply. We're not sure if the NanoStation on the balloon was receiving enough power from the cell phone charger we had it plugged into to hold this steady connection. Another potential reason is radio interference that was around us. If other devices are operating on the same frequency, it would cause interference so that our devices could not communicate by themselves. If the power supply was the issue, I could only think of getting a stronger power supply, that is, if one's available. The NanoStation's power is power over Ethernet, so it's not a very typical way of powering things, especially if you're using like a cell phone charger that you need a few adapters. To fix the problem with radio interference would be to use a frequency that isn't commonly used. You could also try launching in an extremely remote location where there's no interference around you.
My name is Michael Smith, and I was responsible for the Raspberry Pi and Arduino system that made up the main computer system on the weather balloon. Within Within this system, we utilized a Raspberry Pi and an Arduino. The Raspberry Pi was the main form of data collection and ran all of the equipment on board the balloon, including the Arduino. The Arduino was then hooked up to various sensors and devices so that they could measure temperature, altitude, humidity, acceleration, everything that we could possibly gather data-wise on the balloon.
Let's talk about the Raspberry Pi and the Arduino board we are using in this project. The Raspberry Pi is a credit card-sized single-board computer which can do everything that a normal computer can do. And because of its small size, it can be carried anywhere and can be powered using a portable charger. Raspberry Pi also has GPIO pins, which can enable us to interact with the surrounding environment using various sensors. To set up the Pi, we need equipment including an operating system, a micro SD card, a power source, a mouse, a keyboard, and an HDMI monitor. Usually the Pi comes with a manual to instruct the users step by step to start, set up, and use the Pi. In the Arduino board, we use a BME280 sensor which can measure humidity, atmospheric pressure, and temperature. We could easily find the code for the sensor on the internet and use it in our weather balloon. We also plan to use an accelerometer, but we accidentally broke it while soldering.
For the configuration of this system, it was rather simple. The Raspberry Pi and Arduino were simply just linked up by a USB. So setting up the software on a monitor before installing it in the balloon was very simple. The Raspberry Pi was running the Arduino IDE software, which in turn would run the code on the Arduino itself. This data would then be fed into the IDE software and could be viewed through a serial monitor. Thanks to our wireless network, we could view this serial monitor on the ground station that is plugged into the laptop by remoting into the Pi, once again, thanks to the wireless network. What's great about remoting into the Raspberry Pi is that we can use a software called VNC Viewer that allows us to have complete and total control of the Raspberry Pi and in turn the Arduino and see all data collection live and remotely. With this system in place, we have complete control over the Pi and can view all data collection live, as I've stated many times. This should be a simple and elegant solution to long-range and live feed for a weather balloon. However, we soon discovered after launching the balloon that we couldn't maintain a stable connection over a longer range due to the nature of the software we were using. The NanoStation and Lightbeam were intended for private use to extend home Wi-Fi, not space travel. Oops. While we were still able to gather some data at very high altitudes, it just wasn't as efficient as we would have hoped, especially in the long run.